So I'm going to go through what pipes are and what we can do for about 10 minutes, and then we will have a break about 15 minutes, and then we'll come back. So that's how we work. 45 minutes up to 50 minutes, and then 10-minute break, and then come back on for another 45 to 50 minutes. So what is PyPSA? Are there anyone who actually have a chance to use PyPSA before? Doesn't need to be too complex, but simple is fine. Thumb up. Albin, Charles, Abraham, Huma. Yeah, I can see 5 people. They will be a group leader or when we have a group work. Thank you so much for letting me know that. And then I will remember your name, definitely. We are recording this, so I can see your name. You can't get away. So PyPSA is basically Python for power system analysis. PyPSA it's not a solution, it's not a tool at all, it's just a library. And it's open source Python library designed for simulating and optimizing modern electricity systems. And we can do energy system planning, electricity market design, and power system operation as well. PyPSA is an optimization module. PyPSA is a great module and fantastic module, but nothing but just optimization module. You can optimize cost optimal, or you can calculate, you can find the least cost optimization for power plant and storage dispatch and etc. Within network constraint over multiple time period. Here, multiple time period means it can be 10 hours or it can be 50 years of every single hour, but it will take a lot of time if you actually do such a long modeling work. And we can do something like more detailed analysis, like unit commitment modeling for conventional generators, or we can also do investment optimization. So how much do we need to invest in to do this kind of model, to add, let's say, 3 gigawatt of wind power or 5 gigawatt of photovoltaic and etc. That's what we can do using PyPSA. PyPSA is a component-based modeling work. It has multiple components, not just this. If you want to know more about PyPSA, you can simply type PyPSA website, and you can go to component. And if you see those list of components, we have, of course, we have network, and we have sub-network, and we have bus, carrier. Bus is not a car. Bus is where electricity demand or generators are connected. And we have carriers and global constraint, lines, what kind of line types and transformer, link, and load generators, storage unit, store, and others. But in this course, we are going to cover bus, carrier, and then link, load, generator, storage unit. Those are the things that we are going to cover. Those are very basic things that you need to understand, and those are the most frequently used component that you will use. Oh, by the way, if you are sharing just an ID together with your colleague on the same screen, please let us know, because we need to check the attendance, right? And then PyPSA is it's very flexible, which means it is very useful when you do the modeling, but at the same time, it can be very difficult, or sometimes you can have lots of bugs or errors because it is too flexible. And PyPSA is very scalable. So you can make a very simple model, say just one node, and up to 100 different node or more than 100 node. So it can be just an international grid model, which is PyPSA Earth. And PyPSA is transparent. Whoever create the PyPSA model, if they share the model itself, you will know what data they used inside, and what kind of node and what attribute has for what attributes are used for each component and how they are connected and what kind of constraints exist, you will know everything. It's just 100% transparent. So there's nothing you hide behind. So that's why actually NGO or research group likes PyPSA quite a lot. And PyPSA itself is fully open source. If I remember correctly, this is MIT license based, so that you can make closed source or you can make commercial version as well. However, it is not PyPSA culture. In PyPSA world, everyone expect this model is to be open source and shared with others so that everyone can contribute together to make our model more practical and better. So PyPSA has its own server. Unfortunately, we don't need to buy servers. So what, for those of you who don't know what solver is, it's basically a software that is core software that you need when you solve optimization problem, like very core thing. You can create it, but usually it takes a lot of time. And if you create one thing, one very good server, that costs a lot, about 10K US dollars per year. But PyPSA itself has open source server so that we can use it without worrying too much about paying money. And then electricity market, it can do electricity market modeling, long-term investment planning, transmission network expansion, and energy system decarbonization studies. So it is very applicable to too many different way of researches. So whatever you imagine, almost everything can be done in PyPSA. That's the beauty of PyPSA. I will go through 3 more minutes. So PyPSA is basically energy system modeling. You can model AC and DC network. We are not going to cover AC in this course because it's a little more complex, not really complex, but it needs a little more understanding on power system itself. But we are going to assume that entire network is DC, which is much simpler. However, not realistically usable, because not many of you have interest in how reactant and resistant work. And yeah, that's too much technical for this course. And PyPSA is time varying, also can deal with time varying renewable energy generation. So basically you can put the pattern and you can see how this renewable energy pattern work. Also, we can have a storage unit with efficiency and hydroelectricity with inflow and spillage as well. And we can also have sector coupling such as electricity, heat, transportation, industry, and etc. But all of them together in PyPSA. And we can also calculate conversion between energy carriers. When we say energy carriers, it's literally about some sort of concept that carries energy from one place to another place, right? Core is a primary energy. However, it is also energy carrier. LNG is an energy carrier. Electricity is an energy carrier. We are going to this energy carrier concept quite often, but energy carrier is probably not really physically defined concept, but more likely concept. So something that carries energy is called energy carrier. And yeah, so also PyPSA is useful for sector coupling and for flexibility, as I just explained. So that's what we can do using PyPSA. And we are going to have about 15-minute break for my throat and for your sleepiness. Go have some wash and things, and then have some, I don't know, coffee or water, and come back in 15 minutes. I think almost everyone should be here by now, and I cannot see, but yeah, I can see some like reactions. Thank you so much. I definitely want to do this program offline. It would be much more interesting to interact with every one of you, right? So yeah, probably you can send an email to Heinrich or somewhere, I don't know, any funders that we need to do this offline somewhere in Bali or Seoul or I don't know, Jakarta. I don't know, Pakistan, somewhere, recommendation. That would be great. And yeah, let me go through the next probably 15 slide to explain you what is PyPSA, a little more details, and what we will learn during the next 8 weeks with a little more detailed information. And then we are going to have about 10 to 15 minutes to make sure that Anaconda works for everyone. That is very important. If Anaconda doesn't work on your machine, there is no way that we can go through. So if it doesn't work today, then we're gonna have one session to make sure it works, right? So let's go through one by one, and then let's see how it goes. Hopefully, we don't need to have one session. So using PyPSA, we can build a lot of different things. We can actually create a global scale power model and power and energy model, which is called PyPSA Earth. And yeah, let me go here, and then if we go PyPSA Earth, there is a website of PyPSA Earth. PyPSA Earth basically covers entire country, entire world. PyPSA Earth is a PyPSA based framework, so that framework based another framework, so that people can create global scale energy power sector model quite easily. It helps you to get electricity data, build the electricity demand and electricity generation patterns as well. And then it helps you to create a set coupled model as well. And also it is very customizable because it is pipes based. So you can have different different optimization problem, or you can have a different way of running it, or different type of data you can use. So there are lots of examples on this website. You can have a look, but I don't think it will be too much helpful at this stage. But as soon as you know how to use this PyPSA, you can get a lot of information from PyPSA Earth to create your own model with pretty much built on template. So quite a famous model. There are a couple of famous countries that you can see. One is India, and which is built quite extensively. As you can see, all the grid and demand and power generators are already all built in PyPSA Earth. Same for other countries. Must be Argentina, I think. Hopefully, I'm not wrong. And then left side is Chile, so must be Argentina. And then or you can go for entire like continent, so like Africa. Although it's not really as detailed as India, you can see some detailed power grid in Africa, and then also generators around, right? So basically, you have an entire world data set on PyPSA Earth. But as I told you, PyPSA Earth is a framework, so it doesn't actually include the data set. However, it includes modules to cleanse the data or download and cleanse the data for the PyPSA Earth. And also you can use PyPSA Europe, which is very famous one actually. PyPSA Earth is based on PyPSA Europe, as far as I know. You can create international grid model. Definitely, that's something that Planet has an interest in. Planet has a plan to go through next year, from end of this year till next year, to create an Asia model using this PyPSA, which can be interesting to understand how one country's electricity mix changes affect to the other country. Unfortunately, South Korea doesn't have any integrated power grid with countries like China, Japan, or North Korea, because South Korea itself is literally or geopolitically an island. You cannot go anywhere without flying, right? But like Singapore and Malaysia, and there are countries which has international grid, even in Asia, So building up more stronger power network within Asia can be quite useful, or can be a good way to reduce emissions in power sector of entire Asian country, because except China and India, most of Asian countries are not that big geographically, and horizontally is not really wide, probably except Indonesia. So that most of the time, each country has pretty much a fixed single solar panel, solar output, which can cause a bit problem in power market management itself, right? So that having a international grid in Asia can be useful to have more like flexible renewable generation options across entire Asian continent. That's what we would like to achieve. And also, using PyPSA, you can test hourly electricity generation pattern and power dispatch of energy storage. And that's what I am working on at the moment. I can share some of my code, which looks pretty complex, however, not actually that much complex. Like this is one of the output that I'm working on at the moment. This is a power generation or power mix of Jeju Island, which is quite interesting one. However, having some trouble in dealing with market rules at the moment. But these are what we can do using PyPSA. The blue line is model output, and red one is a actual generation output to compare. So I'm doing the validation to match those two almost exactly. However, I'm failing it at the moment, but it always takes time. So as a power modeler, what I can tell you is when you do the modeling, building model itself doesn't take much time. However, validating the model, making it correct, takes a lot of time. So whenever you do the model, you need to put about at least half of your time in validation. It's something different that we will talk later. And also we can estimate the energy storage changes. This orange line, orange curve is a state of charge of a generator. And then we have a blue, which is pumped hydrogen dispatch. So how much it dispatch or how much it charge, and what is the condition of this battery or pumped hydrogen? Does it have enough electricity to, or enough water or energy to discharge or not? So that's what we can do. Also in PyPSA, we can match the start or initial state with the end state, right? So for example, if we fix them, when the initial state is 40% of charging state, then the end state must be 40% for the next cycle. That's how we can actually set the constraint. Otherwise, we will use more electricity than we actually generate during the time, because we have stored the electricity in energy storage system. And we can also do some modeling on zonal using the zonal difference, right? In case of this model, the UK are divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, I don't know, about 20 different zones, so that each will have different amount of demand and different amount of generators, different energy mix and energy patterns as well. And then using the grid model, as you can see on your left side, we can test if this grid is stable or not. So if it's not, how much grid do we need to expand more, or do we need more like energy storage, or do we need more gas? We can test it, which is the most economically usable option. So I think I went through a little faster than expected. So we might have a little more time on Anaconda later. So power model, there are power model techniques that every one of you needed to understand. Those are the concepts that we are going to cover. Let's go through one by one. First of all, as you can see here, this center Give me 1 second. I must be able to have a pen somewhere. Does it need to be slide to have a pen? Ah, can't figure it out. But yeah, this one, each one of these circle is node. So each node can have different generators, right? Intentionally, I only have a conventional generators, no renewables. Sorry about that. So we have nuclear, coal, and gas at the supply node, or called bus as well. You can call whatever you like. Is coal, is bus or node, and then we have demand node or demand bus. So the entire supply must be go through to the demand. That's how the system will work. What is economic dispatch? Economic dispatch is a way to optimize the dispatch of generating units to meet demand at the lowest cost, considering generator constraint. What does the constraint? It explains very complex, right? This is a copy and paste from another explanation, which is very complex. However, what it means is for every single hour or every single 10 minutes, more likely every single moment, electricity demand must be met by any suppliers, right? But in case of economic dispatch, it chose the cheapest one first and then build up one by one. In case of South Korea, if this is South Korea with a renewable, then it will be nuclear, 100% of nuclear, and then it will be used. And if there's any remained demand, then coal will jump in, and then gas will provide a peak. For the next 1 hour, the same will happen, right? That is how that is what economic dispatch means. And this is sorry, I need to admit that Amanda can join. Yeah. Did I kick her out or do we have Amanda? Yep, I think I have. Yep, sorry about that. So that's how we make how we do the economic dispatch. And then we have unit commitment. This is a little more complicated concept. When we do economic dispatch, every single hour is separate, it's individual. So for example, 12 o'clock, we need 100 megawatt of electricity come in, join in, and then coal, nuclear, wind, and solar and gas, everything will submit their like bid, how much they will be paid to generate certain amount of electricity. That's what economic dispatch is. However, in real world, what happens is each generator will have their own specific technical specifications. For example, nuclear power cannot go up and down very frequently. It can, technically it can do it. However, when it does it, it costs more. So that usually nuclear power is just a flat, almost always flat in many cases. However, in Europe, nuclear power can be like France or Sweden. Nuclear power can be flexible as well. It depends on the technical specification. And same for coal, same for gas. Even if they want to generate electricity from 0 to 100%, out of a sudden, they can't because they need to time to heat up the system. Otherwise, and then also need some time to maximize the cost effectiveness because heating up the system or ramping up the system costs a lot due to low efficiency of the system. Sorry about that. And then there is concept called cold start. So when the entire system was completely shut down, when it starts back, it takes time, right? There is time to prepare other things and etc. etc. And then even if you like start up the engine, still you need some more time to start up slowly, to run the engine type big engine slowly or turbine slowly, right? So there is a concept called startup cost and shutdown cost, and minimum up down and minimum up times and minimum down times. Minimum up times means when it generates electricity above a certain level, it must generate at least certain hours, like 5 hours. Then it must generate at least 5 hours. If not, it loses money or something like that, right? That's how this power system works. So when power market operators or bidders of each generator, when they bid their amount of electricity and their cost, they consider all those kind of things, the fuel cost and their specific technical specifications. So we can put all of those together. Then the output of 12 o'clock will affect to the output of the next hour, and then each output will affect to the next hour as well, right? So from the perspective of a generator, their electric generation of 1 o'clock will affect to the next hour, so 2 o'clock and then 3 o'clock and blah blah blah, right? That is what unit commitment is. Then unit commitment is better or more detailed. Why do we need this economic dispatch at all? Because technically, if you want to do the unit commitment, your computer will scream out because it takes a lot of time to calculate each cost-effective optimum. So usually what we do is in case of unit commitment, you run only a certain hours, like peak hours, 1 day, or peak like a week over a year during summer, and another week during winter, and another week in spring and autumn or something like that. Just check it, how it works. It makes sense. And then mostly when you run it, you use economic dispatch. When you run the entire year, you run economic dispatch. Otherwise, yeah, it'll take forever, literally forever. So then next is linear optimal power flow. Explains quite complicatedly. However, what it is basically what it explains is basically Python can consider the power, the power efficiency or power flow limitations constraint. For example, even if we have let's say here, let's assume we have 1 gigawatt of coal and another 1 gigawatt of gas, right? However, if we have a transmission line which can allow only 500 megawatt, then most of those power will be just waste, right? That is what's happening in many countries, including South Korea as well. So for your information, in case of South Korea, electricity should be generated from the south or east of Korea, and they all need to come to northern west of South Korea, which is where Seoul is. But transmission line is not enough. So most of electricity is just wasted there. Not not all, but quite a lot. So that's kind of problem that we need to solve. In that case, we usually use this LOPF, but fortunately in Python, LOPF is calculated in just one step. When you write it later, you will know it when you just type and optimize. You don't need to remember this. When you just type in and optimize, it basically optimizes the power flow and then generation. So economic dispatch as well. And then we also needed to understand what is security constraint linear optimal power flow, which means when there is contingency analysis, when there is contingency issues, which is when a big power generator goes offline out of a sudden or maybe planned, if this grid is still safe, that's what it called security constraint linear optimal power flow. Is very long name, but basically energy security. That's what we say in real world, much simpler and shorter. So what happens if there is one gas power plant lost? Do we still have enough power to provide electricity? So we can do it. One way that we can do is just we can we can assume just one gas power plant is offline. Another way is we can also do stochastic analysis. So we can cover multiple we can provide multiple assumptions to create, I don't know, maybe thousand stochastic scenarios to test how many times what is the percentage of the system that goes entire offline if one power plant lost its capability, right? Um, this is very how would I say real world problem which happened a couple of months ago, maybe about a month ago in Spain, and then a couple of years ago in Adelaide in South Australia, and also in California as well. This is something contingency analysis, which is quite important. And for every one of you, it is all okay to copy and paste this material, but please don't delete it, okay? That's the only rule. Do not delete it or do not change it, because I will not know which one is changed. Also, we can integrate renewables, of course, we can. We only had, that's the reason why we only had a gas, nuclear, and coal. So we can integrate more variable renewable generators with time varying availability, which means renewable energy sources which has a generation pattern to the grid, to the supply. And then we can have a backup gas or hydro power to provide additional electricity, which will be required for the demand. So this is renewable energy integration. Of course, when we have renewable energy integrations too, we can do all of this: economic dispatch, unit commitment, and power flow and constraint. We can do all of those. Of course, we can. We are just building up, and we definitely there is another concept called storage operation and optimization. From the perspective of energy generator or energy modeler, energy storage is always kind of a tricky one to consider very carefully, because usually you have just a demand which is suck up the energy, right? And you have supply which provide the energy. However, in case of energy storage, it can charge and discharge energy with a bit of efficiency losses, bit of electricity losses. Where to so because of that reason, where to put energy storage itself is sometimes very big question, but mostly the biggest question is how much of energy storage is required. The reason is because energy storage usually is very expensive. I mean, when I say energy storage, it's not about hydrogen or PHS, because there are not many places where we can build additional pumped hydro storage in the world entirely. There are some places, but definitely not many places in Asia when we consider the environmental sustainability. But when we see the in ESS system, adding one more megawatt literally requires adding when we have 1 megawatt of energy storage, if we add one more megawatt, then it will require twice the capital cost, right? But in case of gas or coal, it's not technically twice, less than twice. So when it becomes, there is a size of economy of scale, but in terms of energy storage, economy scale is a bit less. So it is need to be careful when we design it. Using this, also we can go through capacity expansion planning, which we are going to do in the week 3, I think. Capacity expansion planning is optimizing the investment plan for the next couple of years or maybe long terms, so that you can estimate how much of capacity is required based on the amount of a investment you would like to put in, or based on the energy required to provide into the entire grid. So that's what capacity expansion planning is. And also, as there will be there was a question on this message about the hydrogen and methane and CO2, and then from Azaria, and then another question from Hyunwoo about the heat pump. Yes, definitely. It is called sector coupling. PyPSA can deal with. We are not going to do it in this 8 weeks because we don't have enough time to cover this part, but definitely PyPSA can do model sector coupling, can model sector coupling, such as electricity to heat, power to gas, or also combined heat and power. So combined heat and power is a generator that provide heat and electricity together. Very efficient. The last one is stochastic optimization. So of course, it is not included in this course because stochastic optimization is pretty much advanced technique and not always useful, because when people say statistics, usually those policymakers and stakeholders don't like it. It's too complicated to interpret anyway, right? So you need just one or two clear scenarios. That's always better, right? So we are not going to cover this. However, if you know how to do it, it will be quite useful for you. We in using Python, we can have different power system, fuel cost scenario in the future. By 2030 or 2050, we can say, okay, gas cost, gas price will go up 1% every single year, or maybe 2%. I don't know, maybe minus 1% or something like that. When you can't really make one clean scenario, we can provide a range, say from minus 10 up to 10% with a median of 0. Do the stochastic analysis, then it will provide you a, a value or result over or result with a scale, so that you can calculate what's the worst and what's the best on your scenario. That's what we can do. Yeah, that's it. I think that's the course of today. And so if there's any question, please let me know. After this, we are going to go through how to install Anaconda. For those of you who already uses Anaconda, it is fine. You can leave or you can stay. It is fine. However, if this is your first time using Anaconda Jupyter Lab, please stay together to make sure that it works, right? Okay. Are there any questions so far? No question? Probably the content was too difficult, or I was just too good. Okay, then we are going to install. We are going to go through the Anaconda together. Because I already have Anaconda on my computer, I'm not going to install it again. But just to make sure that everyone can follow, this is the website of Anaconda. Anaconda is not a spider. Thank you, Charles. And it's a sort of program that allows you to use Python quite easily. It's also called IDE, which is Integrated Development Environment. I will tell you about that part later, but it's very interesting story. There is very interesting story about it. And you can go to the free download. And time your email if you like. If you don't like it, very small, but you can always skip it. Right? See, you can skip it. You didn't know that, but yeah, I didn't know that before. So I registered myself, but fortunately, Anaconda doesn't send you too many email. So it's always it's fine to have it. And there are two different options. One is distribution installer and Miniconda installer. Miniconda installer literally is mini. It's very simple and lighter. However, it doesn't have any single library inside, so that you need to install almost everything on your own. I prefer to have a Miniconda because it's simpler for me. However, if this is your first time using Anaconda or Python, I would suggest you to download this distribution installer. based on your system, Windows, Mac, or Linux. I don't think anyone is using Linux here. Okay, thank you, Charles. Bye. So yeah, here is I installed my Mac version and then installed it. This is everyone followed this part until this part, right? Then you will have this Anaconda navigator. This is where you see the Anaconda. When this is the first screen you will see when you run Anaconda. So do I have everyone so far here? Okay, Abraham, see you next week. Okay. And then there was there was some questions on how to install it properly about the environment. So I will explain you what environment is, how to use it. You can see this environment. Okay? Click it, and there are multiple environments as you can see. What you need to do is create it. But before we create, I will explain you what environment is. Literally, is a virtual system of Python. In case of this, in case of this, this is virtual system PyPSA training. If I write down name PyPSA training and select the Python version, usually I don't prefer to choose the latest one, the second from the latest for the stability reason. And then if you create it, you will have a new environment. The environment is literally the environment where you work on. So in my case, I have multiple, like 5 different environment for different Python. When you use Python, because this is open source programming language, usually you install multiple libraries for your own reason, for your own purpose. Like in case of PyOmo environment, I installed or I downloaded optimization libraries there. For this PyPSA, I have a basic PyPSA module. And for this PyPSA Earth, I have PyPSA and PyPSA Earth and other GIS modules as well. And for this PyPSA Jeju, it's basically PyPSA, but it also includes some local environment as well, local analysis environment as well. So why don't we just have everything on base? Because when you want to share this environment with someone else, if you have everything on base, you will need to share everything that you installed on your computer, on your Python environment, so that it will be very heavy and it will be very, not just heavy, but it will be very difficult to share the environment or share the structure with somebody else. After you have this PyPSA training, you can choose all, right? Then click search package and type PyPSA, PyPSA. I don't have it. Something is not right. I supposed to have a PyPSA here, but it's fine. Let's double check it with here. It's fine. Then let me just double check if I actually don't have PyPSA here. Yep, that's one way. Thank you. And just wanted to check what happened to this Anaconda because I installed the PyPSA using this list a couple of days ago. Py, spy, Py. Yeah, seems there's no PyPSA here. So what we can do is select this PyPSA training and then go to home. And then we will choose Jupyter Lab. Install it. Will not take too much time. Actually, it takes a little more time than I expected. Yes, to Unji, it is better to make a new environment, and then when you make after you make new environment, click it and then go to home. If you don't click it and if you just go to home, most likely you are working on base, right? I would recommend you to make new environment there. And as I must have this one somewhere now. Where's my Jupyter lab? Ah, it's here. Now we have Jupyter lab and we can launch it. Usually when you make a final product, you don't want to use Jupyter lab, but Jupyter lab is a very good place where you can test things, right? And if you open it, you will have this kind of screen. Those are the things that I have already in my environment, which I'm going to close it as I don't need it now. Seems like my internet is pretty slow. Come on. Okay, now we have this environment. We are working on this new PyPSA training environment. And what we can do is we can definitely install it here, but we can also start one of the notebook, start it, and make sure you have PyPSA kernel. And you can, if you like, you can change the name of the file. But what we would like to do is pip install PyPSA. Don't forget this exclamation mark, exclamation, right? It's funny because I'm Australian, but I always forget this word. I mean, yeah, I was Korean and ditched my country after fulfilled my military obligation. I had to do it before. So it is installing the PyPSA. Let me have some time. When it's finished, this mark will be changed to number. Okay, it's done. Because it's too long, now see, it's changed to number. Because it's too long, I'm going to clear it, clear cell output. I'm going to just have one more cell, and we'll see if this worked fine. What you can do is import PyPSA. Discard, yeah, but don't it. Anyway, I have this import PyPSA. So let's see how this, as far as you had no error, when you import PyPSA, means it's fine, this all worked. But just to make sure, N is PyPSA network. If you run it, it says nothing. So let's say, what is N? Empty, unnamed PyPSA network, component, no component, snapshot. That's just one snapshot, which means just 1 hour, right? This confirms that we have a PyPSA here. Okay, this is how we can install PyPSA on your machine. And please go through to make sure that you all have this working machine. If you don't have it, please email me. And if I fail to explain you through the email communication, I will figure it out. We will have a one-on-one session to make sure that, yeah, to have you on board. Okay. Any questions so far?